Hey folks, in this video we're going to be talking about binary ionic compounds and probably also defining binary ionic compounds. So I want you to be able to characterize ionic compounds very generally, and then also very generally characterize binary ionic compounds. And if you're given the name of, or rather the formula of a binary ionic compound, I want you to be able to determine the name. And if you're given the name of binary ionic compound, I want you to be able to determine the formula. So back and forth between names and formulas for these binary ionics. And I want to look at some weird birds. So let's get going. Ionic compounds, as we know, are a combination of cations and anions. They are always going to combine together so that overall they have a neutral charge. This is one of the most important things to remember about ionic compounds. So if I have sodium and chlorine, I'm going to put them together in a 1-to-1 ratio because the plus of the sodium cancels out the minus of the chlorine. It's going to be NaCl. If I have magnesium and chlorine combined together, well, now I'm going to need to cancel out this +2 with my chlorines. So I'm going to need 1 magnesium, and for every 1 magnesium, I will need 2 chlorines. These 2 chlorines are going to balance out and make a total of -2 to cancel out that +2 from the magnesium. And so we can we can have all sorts of different combinations of ions that come together to make compounds. Well, characteristics of an ionic compound, we're going to keep this very general, but in general, they have very high melting points. Very high melting points. These are often in excess of 200 degrees Celsius. Sometimes they can be up in the thousands of degrees Celsius. Ionic compounds will conduct electricity very well if you are able to melt them and make a liquid, or if you are able to dissolve them in water. For instance, salt water is a very good conductor of electricity. Ionic compounds, when they're solid, are usually very rigid and hard. They're easy to snap, but they are very hard to break apart. And ionic compounds typically are formed by lattices that are crystalline. Well, what is a lattice? Here are 2 examples of a lattice showing sodium chloride. We can see these sodium and chlorine ions are very specifically arranged together into what is called a lattice. This makes sure that they all have good contact with opposite charges, and the same charges are not super close together or as far apart as can be. So if we're going to be naming our binary ionic compounds, that's one of our goals. We want to look at a formula and come up with a name. We need to know that they're going to be composed 2 elements always. So that's where this binary comes from. Binary code is 0s and 1s, and these elements are combined in 2s, just like 1, 2, 2 elements, binary. So we're always going to put down our metal cation first in the formula and first in the name. That's maybe because metals are the left, and if we read left to right, metals will come first. Our nonmetal is the anion, and that's always going to be coming second in the formula and second in the name. So let's talk about naming the cation first, because it comes first. The name is unchanged. Very easy peasy. If you have sodium in an ionic compound, you just call it sodium. If you got chromium in an ionic compound, you just call it chromium. And there is something that we should know. Some metals, like these dudes that are not shown in the transition metals here, can have varying charges. We call those multivalent. And so when we have them in a compound, we do need to let the reader know, for writing down a name, what the charge on those multivalent metals are. So for this, we're going to use this thing called the stock system. And it's putting the name in Roman numerals in parentheses after the name of the metal. So if I wanted to express that there is a copper with a +1 charge, I would write copper and put 1 in Roman numerals in parentheses. If I had copper that had a +2 charge, though, I would put 2 in parentheses after the name of copper. Cool stuff. Most of the D block and P block metals have different charges, as we can see. There are only, aside from these 5 fellows here, they're the only 5 that have fixed charges. Otherwise, everything below this thing we call the stair step in white is multivalent. And so, yeah, as I said, there are these 5 exceptions in the D and P block. Okay, let's talk about naming the anion. We talked about the cation, which comes first. We need to talk about how to name that anion, which comes second. Well, the name of the anion is going to be changed. All anions in binary ionic compounds are going to receive, an "ide" suffix. So we're going to chop off the original name of this dude and replace it with an "I." So sulfur becomes sulfide. Nitrogen becomes nitride. We got rid of the whole O-gen there. If you called this nitrogide, I wouldn't hate you. It would be wrong, but I wouldn't hate you. Chlorine becomes chloride. their charges are always going to be fixed. That's the nice thing about these anions. They always have the same charge. Here's a little table representing what our charges fixed for our anions are. Remember, you can go from your noble gases and count over and say, these are going to be 0. These dudes are all going to be -1. These dudes are all going to be -2. These dudes are all going to be -3. If carbon were to get in the mix, or silicon, they would probably be forming -4 charges. Nifty. Oh yeah, there's my carbon. So let's do some examples with fixed charges, and let's try naming these. So this dude is magnesium and sulfur together. Remember, magnesium's name isn't going to change. Magnesium is in my S block. It's an alkali earth metal. It has a fixed charge of +2. So this is just going to be magnesium, and then sulfur is going to become sulfide. So this is just magnesium sulfide. Easy peasy. Yeah, and so it's got a +2 on this charge, a +2 or -2 on my sulfur charge, so I can see here. So they combine in a nice 1-to-1 ratio. Why don't you try coming up with the name of this guy? Pause the video and think about it for a second. Well, let's see. This is lithium, who has a fixed charge, and carbon, who has a fixed charge. All the anions do. So since lithium is not multivalent, I just call it lithium. And then I change my suffix on carbon to carbide, lithium carbide. And this is combining in a 4-to-1 ratio, we can see, because lithium has a +1 charge, if you check the periodic table, and carbon has a -4 charge. So we're going to need 4 lithiums to balance out the charge on the carbon. Let's do some practice problems with some of these multivalent metals. For these, if we're going to name them, there's a little bit more of a process. We need to determine the charge on the metal cation in order to properly name these things. And so to do that, we've got a process. First, we're going to determine the charge on our anion. And then we're going to multiply the charge on our anion by how many atoms of that anion are in our molecule. Or, yes, really our formula unit. And then we're going to divide the result of this step by how many cations are in that formula unit. And then we'll reverse that charge so it's positive. Let's see this with an example. So I've got titanium chloride, but I need to know, is this titanium +1, +2, +3, +4? You might be able to figure this out really easily, but some folks like a nice system, so let's go through it really quickly. So the first thing I'm going to do is determine the charge on my anion. It's chlorine. All right, I need to determine my cation charge. So the first thing I'll do is get my charge on the chlorine. It's a -1 charge. Well, I'll multiply that charge by how many of that anion are in the molecule or formula unit. So there's 4 chlorines, so I'll do 4 times -1. And I'll divide that by how many of the cation are in the formula unit. So titanium, there's only 1, so I'll do my -4 divided by 1. Still gives me -4. And then I'll reverse the charge to make it positive, so that -4 becomes a +4. I now know that this titanium has a +4 charge, and I can call it titanium 4 chloride, because I know it is titanium with a +4 charge. Nice. Let's look at a few more examples with some charges. So here we've got VSE3. Why don't you pause the video and see if you can think about this guy. Cool. Well, let's go through it together. So V, okay, that's vanadium. So that name is not going to change, but vanadium does not have a fixed charge, so we're going to have to figure the charge. Se, this is selenium, so that's selenide is going to be the name. So we got to figure out the charge of this cation. Selenium lives with oxygen and sulfur, so we know it's going to have a -2 charge. I know that there's 3 selenide ions in here, so that's going to give me a total of -6 charge from all of them. Well, I'm going to divide that -6 by 2 because there are 2 vanadiums balancing out that -6. And that tells me that each vanadium must be bringing +3 charge to the party. So vanadiums bring a total of +6 charge. The seleniums bring a total of -6 charge. And I know now know that this is vanadium 3 selenide. Neat. Let's do another example. So we've got Be3P2. Why don't you pause the video and think about this one? Okay, well, in this case, the cation has a fixed charge. I can find beryllium, Be, in the +2s with the other alkali earth metals. So that's cool. Naming this is really easy. It's just going to be beryllium phosphide. I need to take phosphorus's name and change its suffix to "ide." That's the only thing to do here. Cool. And so let's look at this next example. Pause the video. Try this one out. All right, cool. You tried that out? Well, CO, cobalt, is not in any of my fixed metals. It is multivalent, so we're going to need to figure out the charge on that. I know that nitrogen or nitride ions have a -3 charge. I know that there are 2 of them, so the total they're bringing -6 charge to the party. I know that there are 3, that's just vanadiums, but this should say cobalt ions, and those 3 cobalt ions have to balance this out. So we'll do our -6 divided by 3 for those 3 cobalts to give us -2, and we'll switch the charge to say, oh, it's going to be a +2. My 3 cobalts are each bringing +2 charge to the party for a total of +6, and my 2 nitrogens, or nitrides, are bringing -3 to also give us -6. So they will balance out. My formula will be cobalt 2 for that +2 nitride. Okay, wow, the chicken is wearing boots. Those chickens are wearing some sort of garb. Interesting. Let's talk about how we can make a formula from the name of a binary ionic compound. So when we are writing the formula, we're going to write the symbols for each element. So if I've got calcium fluoride, I want to write down my symbols for each element first. This is the process. The next thing I want to do is I want to write down the charge for each element. So I'm going to look those up on the table. And I know calcium is a +2 and fluorine is a -2. If it's a multivalent metal, the charge will be given in the name. So that'll be easy for you. You don't even have to look at the periodic table. Next thing I want to do, and here's the weird part, is I want to cross over the charges from the top to the bottom. I want to cross the cation charge to the anion subscript and the anion charge over to that cation subscript. So my anion is going to become the cation subscript. The cation charge is going to become the anion subscript. Let's see that crisscross. I like to draw arrows for this sometimes. So I crisscross them, I move them down, and then we're good. So now I'm going to remove those charges and rewrite this as just calcium 1, fluorine 2. And then I'm going to simplify the ratio, which I don't need to do here. Here you can see some examples where you might want to simplify your ratio of elements. But in this case, I've already got a 1-to-2 ratio. I cannot simplify that without losing whole numbers. And so the last thing I'll do is I'll remove all the ones. So this is just CaF2. Boom. Not too difficult. Few steps, but not too difficult on the whole. Let's do another example problem. So we'll do manganese 4 oxide. So first thing I'll do is I'll write down my symbols. Manganese is Mn, oxide is for oxygen or O. I'll put in my charges for each element. Well, this formula tells me that manganese is a +4, and I can look at oxygen on the periodic table and know that that is a -2. It's 2 steps away from those noble gases. I'm going to crisscross those from top to bottom. So the 4 will go onto the oxygen, and the 2 will go onto the manganese. I'm going to get rid of those charges, so it's just going to be manganese 2, oxygen 4. I'm going to simplify my ratio of elements and remove the ones. So I've got my removed charges. This can be simplified. I can make this, instead of 2 to 4, divide those both by 2 and get a 1-to-2 ratio. And then last thing I'll do is remove that 1 and get MnO2. This is my formula for manganese 2 oxide. Sweet. Well, here are some other practice problems. Why don't you try and figure out the formula for lead 4 iodide? Okay, cool. Well, if we crisscross our charge of 4 on the lead over to our iodide, which has a charge of 1, we're going to get Pb1I4, and we'll just remove that 1 from the lead to get Pbi4. If we're doing lithium nitride, why don't you pause the video and try and come up with the charge of this guy? Well, lithium has a 1 charge, nitride has a -3, so we'll move that -3 onto the lithium 3, and we'll move the lithium's charge of +1 onto the nitride, so it'll be Li3N1, or just Li3N. And why don't you try this guy as well? All right, well, if we're doing barium bromide, barium has a +2 charge, while bromide has a -1 charge. If we crisscross those, the barium's 2 will go into our bromine, the bromine's 1 will go into the barium, and we'll get Ba1, Br2, which will reduce to Ba, Br. Babber! Anywho, that's the end of this video. That was quite a bit, but I hope you feel like you digested it pretty well and can write formulas you have ionic compounds, binary ionic compounds names, or write names if you're given the formula for a binary ionic compound. Ta-ta! Have a great rest of your life.